Hey everyone, it's Dan Sandig from the Institute for Catastrophic Loss Reduction. Thanks for joining us this morning. We've got a great webinar lined up with Professor Simonovic. Before we get started, I just want to go over the usual routine for asking questions during the webinar. So as usual, we'll take questions via the question and answer function that you'll find in your toolbar on your screen. Feel free to ask questions throughout the webinar, and we'll hold all questions until the end. The next webinar will be on April 21st, and we'll have Professor Ed McBean and Professor Andy Binns from the University of Guelph talking about some of the basement flood protection, backwater valve testing work that they're doing with us at Guelph. So today, Professor Simonovic is going to be talking about practical issues and updating IDF curves for future climate physics versus climate models. Professor Simonovic is a professor of civil environmental engineering at Western University and also director of engineering studies at ICLR. A quick bio, much of his work is related to the integration of risk, reliability, uncertainty, and optimization of hydrology and water resources. Some of his main contributions include modeling risk and resilience of complex systems. Among his many honors, Dr. Simonovic is a Fellow of the American Society of Civil Engineers, Fellow of the Canadian Society of Civil Engineering, and Fellow of the Canadian Academy of Engineering. So with that, I'll pass it over to Professor Simonovic.
Thank you very much, Dan, for the kind introduction. Welcome, everyone. I'm very happy to talk to you today about progress and continuation of our work with the tool developed for updating IDF curves for future. My intention today is to update you on the kind of scientific issues we are trying to continue adding, or scientific improvements we are continue adding to the tool, as well as some of the practical issues in the use of the tool that are coming mostly from the current users in form of questions, comments, and been shared with us through the detailed survey relatively recently conducted by Dan, myself, and the collaborators. For the particular presentation, I would like to thank very much to my close collaborators, Dr. Abhishek Kaur and Dr. Andre Chardon, who did most of the work that I will be presenting on processing some information that we wanted to share with you today. I would like to thank Environment Canada and Environment and Climate Change Canada for assistance in obtaining some data. Dr. Zubin Zhang and Dr. Yo, and help with Dr. Gordon McBean, essentially in obtaining this information, and funding for this work is continuing to be provided by the ICLR and NSERC. Here are the conclusions of my presentation. We are still seeing a very clear practical need for updating IDF relationships for climate change. The practice is still calling and indicating that this is one of the very important tasks that everyone is, at least in practicing engineering, water resources engineering, dealing with. The second conclusion is that the challenges in projecting precipitation extremes remain, and we will need to find a way how to deal with these challenges. One additional comment related to the permanent update and maintenance of the tool developed at Western and now hosted by ICLR was to investigate possibility of considering use of temperature in the process of updating IDF relationships beside the precipitation that's currently being embedded in the tool. So we investigated the Clausius Clapeyron scaling rate use, and we found out that the 7% per degree Celsius clearly does not apply for the stations we investigated across the country and should not be basically used, and we are not planning to add this option to the tool. It seems that IDF CC tool that's based on precipitation better captures uncertainty from the GCMs, And then in the second part of I will be through this experiments and results of this analysis, trying to support these conclusions. And at the end of the webinar, I'm going to focus on the recommendations and how we should do this and how we should deal with these issues in practice. The first recommendation will be to continue utilizing the tool as it is now available with the current updates that I'm going to provide some information about. And also start thinking very seriously about the decision-making process within the context of the issues, the challenges, and especially challenges in projecting these extreme precipitations. So I'm going to talk a little bit more about the move from a risk-based decision-making to process-based engineering, and in that context, switch from basically utilizing risk to a new metric that I'm calling resilience or quantitative resilience. We'll start the presentation with needs of the engineering practice very briefly, and then provide and focus on these two kind of issues: comparison between the precipitation-based tool, our IDF tool, and physics-based temperature scaling, describe the experiments we performed, present some basic results from these experiments, and then switch on the discussion of the kind of practical issues that are arising from the uncertainty being involved in this process, and needs for a kind of new decision-making paradigm that will be able to I am sorry about my voice. Needs of for the new decision-making paradigm that will be able to kind of address the uncertainty. I'll end up the presentation with these two suggestions: how to move from the risk-based to performance-based engineering, and how to consider replacement of risk by resilience. So to make the introduction short, almost all the water resources engineers are on a daily basis utilizing intensity, duration, frequency information in their practice. The product on the left-hand side, the graph, is a typical product provided by Environment Canada, which relates the duration, intensity, return period of the extreme precipitations, and basically provides the main input into most of the water resources planning, design, and management activities. The problems are occurring with the fact that this particular product is developed utilizing historical information, and in the kind of current and non-stationary world, we are realizing that the history will not be the best representative of the future conditions. As illustration, I picked up some of the extreme rainfall events that were occurring across southwestern Ontario from 2004, Peterborough, then Toronto 2005, Hamilton 9, Mississauga 2009, and GTA in 2013, and how does precipitation events, extreme events, compare to 100-year design storm or the Hurricane Hazel, which is still considered to be the design. And as you can see in the last column, the very, very clear message is there that 1 hour maximum intensity with all these 5 events exceeded the design storms. So utilizing the kind of historical information and tools like IDF tools provided by Environment Canada requires some additional work, and municipal engineers as well as other water resources practitioners are calling for some assistance in trying to see how to update the rainfall IDF information in order to address this longer term potential change and impact of climate change on the process of updating IDF curves is quite technical, and many of the locations where the needs exist do not have expertise and resources, and that motivated the work and development of the tool that we completed and made public in the beginning of 2015. However, the development of the tool as well as the procedure for updating is still full of challenges, and the challenges are coming from the fact that we do rely on assessing the climate change in the future on the modeling tools provided by the climate community. In this slide, I'm trying to illustrate how different tools, different models, especially global climate models, which are considered to be the state of the art in climate information, are providing very different information for the kind of same location. In this graph, you can see for one of the emission scenarios, the variation in the precipitation, which is predicted by the various tools in different colors. And in the bottom graph, similar for the location is London. For this one emission scenario, again, various tools predicting the change in temperature. So one of the very important messages coming from this fact that we have to deal with the issue that this process of updating or process of addressing climate change and finding the impacts of climate change on water resources management is subject to this kind of process uncertainty, which is being introduced by the capability and of the current tools, models to predict the changing conditions. In summary, the kind of very important message being observed is that the variation, especially in the precipitation over the predicted period, let's say until the end of the century, is showing much more noise than the prediction of the temperature. And I think this is the kind of motivation for looking into different ways of updating relationships, either utilizing the precipitation or the temperature. The current options are relatively limited. We see that precipitation is being used by our tool that's available and being used across Canada, as well as the other tools that are available. The main difference is that the other tools that I was able to identify, Ontario Climate Change Data Portal and Northeast Regional Climate Center at Cornell University, are utilizing precipitation and regional climate models, whereas we are using the climate precipitation and global climate models. As opposed to that, nowadays, the temperature is being suggested to be considered, justifying this by the closer kind of physical relationship that underlines the possibility or the relationship between the temperature and the extreme precipitation. And that's exactly what was the main objective of the first part of this presentation, to investigate the benefits or the potential utility of utilizing temperature. Let me quickly review the tool, just to remind you. I think we had webinars before that were talking about the tool and the development of the tool, as well as some of the results of the use of the tool. Currently, I think I pointed out the tool is available since early 2015. It's in a web-based format and accessible to everyone. Requires registration. We currently have about 730 registered users, which are utilizing the tool pretty intensively over the year. Approximately 600 sessions were recorded, approximately 760 Environment Canada stations analyzed, and users were adding their own stations for which the data was provided by them, and you can see 130 stations being added to the tool. We performed a detailed user survey recently. The paper is under review that kind of looks into the detailed outcomes of the survey. And we are in touch with people who are using and posing questions related to their kind of use of the tool, trying to kind of update and work with the tool and work with the potential users. Some difficulties were obviously related to the way of hosting and having budget to do that, because tool was developed utilizing the research budget over the fixed period of time. I am extremely thankful to ICLR for deciding to host this tool and provide some modest budget that we can continue updating it and doing our best to serve the needs of the community. So the tool database is permanently being updated, but we are also working on a serious improvements and trying to answer the questions and requests that are coming from the users. The tool is pretty well documented. Number of papers, technical user manuals are all available, and hopefully can help users in utilizing the tool. Recently, physics-based temperature scaling is proposed as a kind of more robust approach than utilizing the precipitation in our tool. And this information is being shared at some kind of meetings, and that prompted the analysis that I'm going to present here, and basically our investigation to see is there a value in trying to add the physics-based temperature scaling to the tool and maybe expand the options for the potential users. Before I proceed with that, let me just remind you that in our tool we have two main kind of theoretical contributions incorporated. First one in comparing the various climate models and assessing some kind of skill based on the quantile regression skill score method that looks at the distribution features, characteristics of the distribution features, as well as the temporal features or bias. We are not recommending use of this skill score to select a single GCM model in the process of updating the tool, but this could be an indicator, which model at which location provides a little bit better results. The most significant part of the tool and most significant theoretical kind of background is the downscaling procedure that we implemented to bring the basically global data to the needs for developing the IDF curves. And this procedure is based on the so-called equidistant quantile matching algorithm that performs the spatial and temporal downscaling by basically developing the relationships between the daily maximums based on a baseline GCM distribution and future distributions on one side, and then also relating the baseline GCM daily maximum to sub-daily historical observations on the other side. We opted to use the Gumbel distribution because this particular distribution is the distribution of choice by Environment Canada. And if the historical curves are available in that form, we thought the updated curves should be also developed in this form. We fully realize, and some of the work that I have done about 7-8 years ago did show that there are distributions that can be maybe a little bit better for this particular purpose, but that's maybe a topic for another discussion. However, the use of the Gumbel distribution ended up in a very attractive mathematical kind of outcome that relationships investigated and established in this spatial and temporal downscaling in the case of the Gumbel distribution end up being in a linear form. The tool includes a database that contains 700 Environment Canada stations. The users have opportunity to provide their own stations and data. The database includes 24 GCM models. Out of 40 and so available GCM models, we selected all the models that provide the data for all emission scenarios, 2.6, RCP 2.6, 4.5, and 8.5. RCP 6 is not included because it is obtained by interpolation between the 4.5 and 8.5, and it's possible relatively easily to do that. And all the available GCM runs are included in the database. Database is permanently being updated as the new kind of information and data is being posted by the climate community. We immediately update our database so that the user have the most recent information. User interface is built in a relatively friendly form, utilizing Google Maps that allow, for the selection of the station, manipulation of the data, identification of different locations where the data or stations are located, or the stations will be entered if the users own their own data. We have also we utilize the interface to manipulate and present the results in various forms, graphical, tabular, and so on, basically making the tool relatively easy to use and producing the information in a very similar form to the product that users are used to that's provided by Environment Canada. The third main component of the tool is the model base, and in the model base we store all the kind of statistical analysis algorithms, the skill score algorithm, the updating IDF updating algorithm. We have also optimization model involved in it because the point calculated values are fitted to distribution, and we utilize the optimization algorithm to find out the basically parameters of the fitted relationship. Let me now start with the discussion of this comparison. So in order to kind of assess the utility or potential utility of the physics-based approach, we looked into use of temperature as a predictor for updating IDF curves, as recently being suggested by some experts. The basic assumption is that the increase of precipitation extremes at rate of 7% per degree Celsius is acceptable or should be used assuming constant relative humidity, as indicated by the Clausius-Clapeyron relationship. The background of this assumption is that it's based on kind of physics, and it should be lowering the uncertainty in the projected IDF curves. To test that, we created two experiments. In the first experiment, we proceeded with analysis of the empirical relationships between daily maximum precipitation and daily temperatures in comparison with the 7% Clausius-Clapeyron scaling. And in the second experiment, we actually developed the IDF curves utilizing our tool and utilizing the theoretical Clausius-Clapeyron scaling with 7% rate, and perform the comparison. This work resulted in a really a large number of outcomes, and results are available for multiple models, emission scenarios, locations, and I will be only kind of showing briefly the kind of key results or key messages that we were able to obtain in this process. Just to provide some basic background on this kind of physical-based approach, the Clausius-Clapeyron relationship describes the increase in the saturation of water vapor pressure associated with warming. This value of ES is, I am sorry, allow me to have a sip of water. In the August-Roche-Magnus approximation, the saturation of water vapor pressure can be related to the temperature in the degrees Celsius, and the whole message is that this relationship is in a kind of exponential form. Assuming the constant relative humidity, this would lead to kind of an increase of moisture available for rainstorms at the rate of 7% per degree Celsius. There is a literature that IPCC last report is also mentioning this particular relationship, and we wanted to investigate how reliable is this 7% increase, or can that be implemented in our conditions? So the following experiment was created. We utilized the observed short duration daily precipitation maximum and average daily temperature, and looked into relationships to extract and validate the information against the Clausius-Clapeyron scaling rate. In this process, we looked for stations across Canada for which we were able to obtain the detailed sub-daily measurements varying between 5 and 30 minutes and 1 and 24 hours. And we also went for the stations with a longer record, exceeding 30 years of measurements, covering different regions of Canada, as you can see, East Coast, West Coast, including London and Brandon, to cover the regions in between. And here are some of the basic findings. What you see in this set of graphs that I'm going to show for a particular duration, you see the relationship between the temperature, which is on the horizontal axis, and the precipitation in a logarithmic form on the vertical axis, where the dashed lines are showing the 7% rate relationship, and the full lines are basically showing what the data is obtaining. The dots are basically the real data. The colors are indications of the green 90 percentile, blue 95th percentile, and red 99th percentile. So for Moncton and duration of 30 minutes, you see that the 7% rate seems to be fitting pretty well. However, with the increase in the duration, this is the data is starting to kind of deviate from this 7% relationship, and with the even longer duration, the deviation is much stronger. The similar observation is generated, or the results are generated for London. This is for the 30-minute duration, where some similarity with the 7% exists, and slow departure for the longer durations of 6 hours and 24 hours. For Brandon, Manitoba, again, 30-minute durations are relatively close to 7%. And 6 and 24 hours, again, pretty far. And finally, for Vancouver, we noticed, quite huge difference between the 7% and the real data from all the durations: 30 minutes, 6 hours, 24 hours. Very strong, actually negative slope for the temperatures exceeding 10 degrees. So in summary, the subdaily maximum precipitation shows very weak linear correlation based on the analysis with these 4 stations and all the historical data available. We only found that lower durations for Moncton, London, and Brandon show some closeness to 7% per degree rate. For Vancouver, this was not even present. And in conclusion, I think we can say that the Clausius Clapeyron scaling rate does not apply for the stations that we considered, and should not be kind of used to derive the IDF curves for the future. Second experiment, as I pointed out, was aimed to look at now into uncertainty. And what we have done, we basically utilized 358 selected stations across Canada. Again, the stations were selected based on the length of the record, and we used only stations with record longer than 20 years, and then calculated two important indicators. One was a difference in projected changes in the form of the total precipitation, and another one is the difference in the projected uncertainty. And the main objective was to kind of compare this physics-based or Clausius-Clapeyron 7% rate versus IDF curve based on, or IDF tool based on the precipitation. And we covered all RCPs, or all emission scenarios, from 2.6 to 8.5, all return period between 2 and 100 years, and all durations between 5 and 30 minutes and 1 and 24 hours. So lots of information is generated for all these 358 stations, and I'm going to try to illustrate the kind of outcome by explaining what the summary graphs are showing. So for each location, each return period, each emission scenario, each duration, we calculated the IDF curves using both methods, the physical-based, temperature-based method, and our tool, which is based on the precipitation and global climate models. In this particular graph, I'm kind of showing the difference between the two. So the red range shows the range of IDF curves generated from all the models, all emission scenarios, all durations, utilizing the 7% Clausius Clapeyron, and the blue range shows the range of IDF curves generated using our tool. The full black line shows the median for the theoretical range based on temperature, and the dashed black line shows the median for the IDF tool-based. So as you can see, in this particular case, there is a difference in the range being generated. There is a difference in the kind of upper bound. And for different emission scenarios, thus, obviously these two methods were showing different results. We tried to summarize the message somehow, and that message was kind of presented, as you will see now, in the two forms. One is form of the difference in projected changes, where we basically normalize the difference between the precipitation obtained by the Clausius Clapeyron 7% rate and our tool, and divided by our tool. And the following three plots for RCP 2.6, 4 plots for emission scenario 2.6, 8.5, 50 years and 100 years return periods for one duration of 24 hours are basically showing that difference. The difference is presented in two forms: in the direction of the small triangles, which are basically pointing to the locations of 380 stations that we considered, and the color that's attached to each of the triangles. The triangles pointing up are indicating that the projected changes using the theoretical or the temperature scaling are showing the wider range than the IDF, or the range of IDFs obtained utilizing the precipitation-based IDF tool. The color is pointing out the percent difference, and you can see, utilizing the scale, that for the 24-hour duration, 50-year return period, and the emission scenario 2.6, we have a kind of mixed bag of outcomes at certain locations. The precipitation-based tool is showing the wider range. At certain locations, the temperature-based is showing the wider range. However, when we move to the longer, to the more extreme emission scenario, the message is becoming a little bit more kind of, or a little bit stronger, in the sense that the temperature-based assessments of the IDF curves are providing a wider range of uncertainty. Very similar message for the 100-year return period. For the 2.6 emission scenario, the kind of mix across the country, and for the emission scenario 8.5, again, very similar, pointing that theoretical or the temperature-based assessment is, still subject to pretty wide or pretty high level of uncertainty. In the second attempt, we tried to actually measure that projected uncertainty, and what we did, we utilized the 5th and 95th percentile and the difference between them as one of the relatively commonly used in literature measures of the uncertainty, and then we compared again the Clausius Clapeyron 7% versus IDF tool divided by the IDF tool, and tried to present the results for the same two emission scenarios, 2 return periods and 24-hour duration. I am just going to repeat that this information is available for all emission scenarios, all return periods, and all durations. So we have many maps and lots of information available for those who may be interested. We're also working on 2 papers trying to summarize and publish these results for the broader audience. In the case of capturing the uncertainty now, the message is a little bit different. For the I am sorry, for the emission scenario 2.6, now we are seeing basically that the theoretical or the temperature-based approach is not picking up the kind of uncertainty or the whole range of uncertainty that's being introduced into the process by the various climate models or utilization of multiple models. For the 8.5, the picture becomes kind of mixed, and we see that both methods are still bringing certain level or describing the certain level of uncertainty. For the 100-year return period, very similar. For 2.6, we have a very clear message that I think IDF is better describing the uncertainty or picking up the uncertainty, and in 8.5 against the mix across the country for different locations. That brings me to kind of summary of this. Summarizing these results is a little bit harder than in the previous experiment. What we can say is that the theoretical Clausius Clapeyron scaling, 7% scaling, is resulting in higher values of projected changes for the future compared to the IDF tool for 4.5 and 9.5s, especially in the central Canada. For 2.6, results are quite mixed, and for 2.6, IDF results are, the tool results based on the precipitation are resulting in a lower uncertainty than for the 4.5 and 8.5 more extreme emission scenarios. Conclusion is that we feel that precipitation-based or our tool is better capturing uncertainty that's being introduced into the process from these various models. And I think the kind of wrong impression that the 7% Clausius Clapeyron will be resulting in a single future IDF is not kind of possible. The uncertainty range obtained or observed in the IDF curves calculated based on that may be even larger than the uncertainty range resulting from the precipitation-based IDF tool. So now we are arriving at the kind of key question. So what should we do? And I think the kind of two conclusions are very clear. One is that we have to live with this process uncertainty. Bringing the climate change into the water resources management activities and engineering today will basically require considering and continue making decisions under the pretty high level of uncertainty. That, I think, prompts another conclusion that we need to focus on the modification of the decision-making process in order to address that uncertainty. In the same time, I would like to bring the kind of key questions that we got from the people who are utilizing our tool. And the questions were along the, they can be kind of grouped along these three key points. One is there a way of standardizing? Is there a way of kind of recommending one particular model, one particular emission scenario? Can we actually help the community in a way of reading that uncertainty range and selecting, one potential recommendation out of it? The second one was, okay, if there is no way of doing that, how can we deal with uncertainty, especially how can we communicate and understand better the consequences of the uncertainty that's definitely present in this process. And the third question that we are very often getting is, what to do for the situation or the locations where we do not have observations. We are engineers. We are dealing with this question, I think, since we started our profession, and I think this question will be very hard to avoid because we will be continuing implementing infrastructure, building, designing the locations where we do not have the observations, and we need to find a way how best to provide the inputs for these engineering activities. I would recommend that we continue with the utilization, especially when the IDF updates are required, continue with utilization of the precipitation-based tool, our tool. and that we focus on utilizing the results from the tool in a modified decision-making process, which will be kind of moving from the risk-based decisions to something that I call the process-based engineering or process-based decisions. And in the same time, switching from the single value of risk to resilience, which can provide a little bit more information that will feed into decision-making process and better explain the uncertainties associated with the inputs into the process. This is an example of the regulatory approach or the standardization. I'm not saying that this is the way to really go, but for example, the Prince Edward Islands Transportation Infrastructure and Energy Department decided to provide the guidelines in the form of advising everyone for the new developments, new subdivisions and developments, that use of the future climate data is required. They're explicitly saying that University of Western Ontario tool is one of the tools that can be used in this process. They are not saying that this is the only tool that should be used. However, comparison with other tools is advised. And they even went further to suggest use of ensemble of all models and generate the information for the two emission scenarios, future emission scenarios 4.5 and 8.5. The second kind of attempt that we made to deal with uncertainty, especially communication and helping understanding uncertainty, is enhancement that was added to the tool to basically in the form of this type of box plot show the uncertainty that's associated with various use of various models in assessing the IDF curve. So this is IDF curve for one particular return period and duration and one emission scenario, and the whiskers around the box plots are showing basically the range or the uncertainty level that comes from the availability of multiple models, multiple runs of these models that are part of the tool. So this is one way of kind of showing the results and maybe bringing the understanding or maybe bringing the information about the uncertainty a little bit closer to the user. Another practical advice that I was kind of commonly providing in the presentations where I was talking about or asked to talk about the tool and to talk about how to bring the climate change in water resources management is actually to utilize the whole range of the outcomes that tool provides and look at the, look at this range as a kind of source. It is a source of uncertainty related to the process, but look at that in a decision-making context as a kind of information on the possibly conservative solution versus less conservative solution. On the right-hand side, you can see two kind of outcomes. This was a work done for the City of London on looking into the impacts of climate change-caused flooding on the municipal infrastructure. Aggregated measure of risk is shown in the different shades of red, and graphs or maps are produced for kind of extreme situations, trying to point out first what will be the difference in risk, in intensity or the level of risk, as well as the location, and also giving us opportunity then to look at the decision making based on this risk in the context of what the potential impact of that risk will be. Are we talking about potential threat to life? Are we talking about serious economic damage or any other social or environmental impact? The decision makers can now kind of walk between these levels of risk and make their own decisions. We tried also to help a little bit with the question of the ungauged sites based on the information the tool is right now providing. We performed a spatial interpolation of the data and mapped that across Canada, helping users to possibly for different models, different emission scenarios, and different precipitation durations and return periods, identify what will be the range. This information is strictly based on the values calculated at the Environment Canada stations, and therefore, the density of the stations, and we know the difference between the southern and northern parts, is, very, very strongly affecting the results. Therefore, we decided to proceed with a much more serious consideration of this question, and the work is now being very close to be fully implemented in the tool. We actually are developing the gridded product that will be attached to the tool. It's tested using the historical data, and on the grid 10 by 10, we related the mean annual precipitation, maximum annual precipitation, and mean annual convective available potential energy, and linked them to the precipitation of different durations, from daily to hourly and sub-hourly. We investigated various forms of relating these variables, from linear and then quantile regression and generalized additive model, evaluated utilizing various criteria, tested this on 526 stations across Canada, and prepared the material, the paper for the journal to get the peer review and outside opinion about this particular approach. We are expecting this to be done very soon, and the implementation is already in progress. That will add to the tool basically another piece of information, map like this, or basically information in numerical and graphical form for each grid cell of 10 by 10 kilometers covering the whole territory of the country. Let me get close to kind of finishing the presentation. I would like at the end to talk about the need to adapt the decision-making process in these circumstances. We have to consider, and I made my suggestions into these forms, that the uncertainty is going to remain present in the process, and that the process will need to kind of move from the prescriptive and typical, risk-based information or risk-based decision-making to something that will be looking into functioning and performance and the details of the engineering system we are dealing with in the kind of process-based form. And that will allow for move from risk to the resilience. So this idea of the process-based engineering is now emphasizing the value of bringing systems analysis into the water resources engineering. We will be able, by better describing the process and elements of the process, relationships in the process, to link the system structure to system performance, and switch from the probabilistic to kind of deterministic type of simulation. Our colleagues in earthquake engineering are already kind of making some progress along that line. And seriously trying to suggest move from the kind of probabilistic standards and codes to process-based analysis. If this is particularly, if this is kind of acceptable, then the idea of moving from risk will, a single value of risk will allow us to pick up or develop or utilize a new or innovative criteria for the decision making in the form of a resilience that is describing in a dynamic sense the performance of the system and the adaptive capacity of the system to kind of respond to changing conditions. These two graphs are kind of picking up the main idea behind the resilience, where you are replacing the single value of risk with now graphical, dynamic function that describes how the system responds to changing conditions, here represented as a disturbance, and then the change of performance, which can be measured in various units. Disturbance could be flooding, and the performance could be, let's say, the inundation of kilometers of the roads or number of buildings and so on. So by looking now this kind of performance or the response of the system to disturbance that can be obtained through the detailed type of deterministic simulation, we can calculate some new measure. The measure is named in our research as the resilience, and represents basically the area, integration of the area under the system performance curve, in a way indicating the level of remaining performance in the system as a consequence of the kind of changing conditions. Now, this is not directly visible, but this type of metric is providing much more insight and information about risk and performance of the system. We are not seeing now the consequences of the uncertainty in the form of the kind of single number or single color at a particular location in the city of London as I had before, but we can actually see the kind of slope of this particular curve, which will be telling us something about the redundancy of the system. We can see the kind of depth of the maximum loss of performance or the remaining functioning of the system in the form of the robustness. We can see the slope of this kind of rising curve as a measure of the resourcefulness or the ability to mobilize material, human and other resources to kind of respond to the changing conditions. And we can also estimate and see now the time which will be required for the system to fully kind of come back to functioning. So you see that now you have already four kind of different indicators, four different elements of this metric that can really provide a deeper understanding of the consequences of the changing conditions or the uncertainty, and also gives us opportunity to come up with the decisions that we will be better addressing. So that brings me back to my conclusions. Then, in my opinion, there is a clear practical need for updating IDF relationships for climate change. The challenges in projecting precipitation extremes remain. Use of the IDF CC tool developed by us and now hosted by ICLR is still a recommended option. I feel that Clausius Clapeyron scaling utilizing 7% per degree clearly does not apply for our conditions and should not be used. And that IDF tool kind of better captures the uncertainty involved in this process of bringing the climate change to water resources management. And ending with the recommendation to, beside you continue using the tool, understand and be prepared to live with the process uncertainty, and possibly think about moving from the risk-based decision-making to process-based decision-making, which is kind of bringing us to use of the simulations, usually deterministic simulation combined with a new metric like resilience, and offering decision makers deeper understanding of the uncertainty and possibly a better way of reaching decisions that will be necessary. Let me end up with some of the resources. I didn't talk today about use of different distributions, but we did a considerable amount of work of looking IDFs and use of the different distributions. So these are some of the publications that are being available. Some of these are very, very popular. My laboratory is publishing the water resources research reports. They're distributed through the university library. And we have approximately 11,000 downscales from the, downloads from 2011 since the report was printed, and the number of publications in journals and so on. The second source are the information about the IDF tool. We are continuing, we obviously published the basic theoretical principles embedded in the tool. We also published the information about the tool development process, which was a participatory process, and we described the process, as well as the documenting the use of the tool and the implementation of the tool to look at a little bit the Canadian conditions. Recently we submitted the paper that we expect pretty soon to be out, that looked into results of that detailed survey of the users of the tool. And the final set of publications that I would like to bring to your attention is related to this new metric for dealing with kind of uncertainty in process-based type of engineering resilience. We implemented this measure in looking the kind of flooding in the coastal megacities, especially the city of Vancouver. We also talked in general about the methodology, and then looked into implementing the same measure to look at the dynamic resilience of multipurpose reservoirs. With this, I would like to thank you for your attention. Most of this information or resources are available directly through my website, looking under the research and publications, or following the path to my laboratory, where you can find all the material that's publicly available. I will be very happy to answer some questions. Thank you.
Okay, thank you very much, Professor Simonovic. I just want to remind everybody where they can find the question and answer box. It's on the top left of your screen in the toolbar. Feel free to enter some questions when you have a chance. So about a few questions here. So you had a number of your experiments earlier on, and your graphs are showing a pretty big divergence in the Clausius Clapeyron relation and the IDF-CC tool outputs. And those were for rainfall events up to 24-hour return periods. And as you mentioned, as the duration increased, so did the divergence. Do you think that there is any application for the Clausius-Clapeyron relation for even longer duration events, for say multiple day events?
Okay, then I have to correct the question. These graphs are basically showing not the comparison between the tool and the Clausius-Clapeyron 7% rate. They're showing the difference between the real observation of the short duration precipitation events from the observation data with this theoretical relationship between the temperature and so this is illustrating, or these graphs are basically illustrating the validity of this assumption that the rate of change is 7% per degree Celsius. First, we are seeing that the rate is not linear for almost all the stations being analyzed and all different durations. And second is that we are seeing that there is a very significant deviation from that 7% linear rate. So I will be having a very it will be very hard to actually justify the use of that.
Right. Okay, understood. Sorry about that misinterpretation.
No, that's okay.
And so I guess the other part of the question was, so those are for up to 24-hour duration events. Any thought on even longer duration events, say multiple day events, if you have a sense that it would become continue to deviate, or is there any practical use of the other approach for longer duration events?
I would have it will be speculation on my side to say that this is exact presentation of the data, and there is a possibility of relatively easily performing this analysis for the longer durations. But our focus here in the IDFs is on the durations which are shorter than 24 hours, and basically, especially these very short durations, sub-hourly durations, where we have difficulties and lack of information or lack of predictions in the future. Most of these kind of climate models are providing predictions up to daily, and some are now on regional scales, and also trying to work and improve and move to a shorter temporal scales. But I don't see in the foreseeable future that this information or the future predictions will be available on simply that short scale. The reason being that description, the basically description of the physics and the character of the precipitation, short-term precipitation events is not yet fully incorporated in the climate models, as well as there are some I think difficulties in understanding all these short duration or the physics behind the short duration precipitation events.
Okay, thanks. So we got some more questions online here. One is about use of scenarios, and perhaps a question about why certain scenarios are in the tool. So what is the practical purpose of estimating future IDFs for scenario 2.6, which is not business as usual for global mitigation targets?
Okay, we incorporated 2.6 scenario because it's one of the scenarios that the climate community is still kind of keeping as a kind of four main visions of the future. I fully agree that the literature is already saying that this scenario may not be of interest anymore, because what the predictions that are under these particular scenarios are already being kind of exceeded. So the value of having four scenarios and having this is to actually see the potential range, and that range of uncertainty that I'm re-emphasizing exists as a consequence of the process and the consequence of the fact that we have multiple models, and multiple models result in, or provide the information in various provide various values. And to fully kind of understand that range of uncertainty, I don't think it's bad to look at the range starting with 2.6 and then going to 8.5. Okay,
thanks. Couple more questions from our online participants. One is, how are you addressing spatial uncertainty in local convective precipitation for extremely short durations?
We are okay. So the way if I consider this to be related to our model, or sorry, our tool. In our tool, we are utilizing this downscaling approach, which is a purely statistical downscaling approach that relates the historical short duration precipitation to the daily precipitation values. Through these relationships, we are basically finding the regression between these different values, not going into the kind of physics and what will be happening on this, spatial, or how the spatial variability is getting into that process. The information that history or historical observations are bringing are in a way bringing into the tool and into the process, downscaling process, that spatial variability. Because we are utilizing the observations at all stations, all the kind of historical data, assuming that the measurements at the stations are representing the difference between different locations, and that's directly being utilized in the development of this statistical relationships, downscaling relationship.
Okay, thanks. Another question from a participant. For short duration, model simulated extremes do not behave like the observed extremes. How can this be resolved or addressed in projections?
Can you repeat the question once more, Dan? I'm not sure that I'm catching it.
For short durations, model simulated extremes do not behave like the observed extremes. How can this be resolved or addressed in projections?
Okay, so again, I think this question goes a little bit deeper into, or requires a little bit deeper explanation of the downscaling procedure. I would suggest the person who asked the question maybe to look into our publication from 2014 that provides a very detailed description of the downscaling process. What we have done to address that difference between the history and the future is the way how the downscaling is performed. And I think one of the graphs did show that we developed the two relationships. One is relating the daily values generated by the GCM models for the historical period with the daily values generated for the future periods. That's one relationship. Another relationship is between the daily values generated using GCM models for the historical period and historically observed sub-daily information. So this relationship is then transported and obviously used in the future. And by utilizing the GCM models to generate the basic daily information, we try to provide kind of background for information or transfer of that information into the future.
Okay, thanks. And so getting on to I guess the sort of second part of your presentation, you talked about a different approach
for decision.
I guess decision-making, engineering practice to account for uncertainty. So the one approach, the sort of typical approach, I suppose, you mentioned is standardization, and you gave the example from Prince Edward Island. A lot of the discussion going on around climate change adaptation is sort of applying this approach, for example, generating standardized advice on how to update data for climate change adaptation, that sort of thing. So two parts of this question are, explain a little bit more of the drawbacks so people, I suppose, are clear of this approach, because it seems to be a pretty common approach. And then on the resilience approach, can you describe a little bit how, as sort of how engineering practice might move toward this approach? Are there any examples of people applying this approach now?
Yeah. Okay. I think this is a very good question and probably requires another webinar. If you allow me, I would like to bring that graph that shows resilience and. Okay, so the first point that I'm trying to make is we observed, at least through this analysis of the updates of the IDFs, that the future predictions are subject to considerable uncertainty. In this analysis and in this presentation, I focused on the process uncertainty that's being introduced by the ways how we bring the climate change to a local scale and provide the information for engineering decisions. That this uncertainty can be replaced with a kind of single message by some standard and saying, use the median, use the ensemble, and that's it. By illustrating how wide is this range of uncertainty, I will be hesitant to support that type of approach. But this is basically a traditional way how we do engineering. And I think because the uncertainty will not be present only or will not be introduced only by the process. We will be facing uncertainties in other aspects that are affecting, let's say, hydrologic cycle through the change of the land use, through the change of population demand, and so on. So the uncertainties from all sides are going to be kind of integrated in making our engineering decisions pretty difficult to make and push us in the direction that we have to consider that. And this is where I see that, use of a single standard. We are traditionally designing pipes for particular return period, particular duration, and you take, the IDF curve based on historical information, and you have a single number. That I don't think will be sufficient for the engineering activities in the future. This pipe will be in the ground for next, 50 years. We are fully aware that the conditions are changing. And what I'm kind of trying to introduce here is that we should be looking now, what this pipe will be doing, what and how this pipe will be part of the overall, let's say, drainage system, if you are talking about drainage pipe, and how this pipe will perform as a piece of infrastructure under the changing conditions. So this is the reason, and this, I think, justifies the use of something like this, where the functioning of the system or the pipe in the system will be described by a simulation model that will capture the structure, the elements, the links between the elements, allows us to implement various inputs. The inputs can be representing these changing future conditions, and then assess the performance of the system, which is basically the results of the simulation over time, by using the measure like resilience that actually contains a lot of information, lots of information about the system, the way how the system will be affected by the changing conditions, the way how the system will continue functioning subject to these changing conditions, and use this criteria as a potential to make two types of decisions. First type related to system structure, basically design of the pipe, size of the pipe. The second decision, how will the system be operated, and how will the system be functioning if particular conditions like precipitation conditions change over time. So by experimenting with the simulation model and the measure and utilizing this kind of performance to calculate the measure of resilience, you are getting the deeper insight and understanding how the changing conditions or uncertainty may be affecting your decisions, and use this as one of the decision-making criteria. So the objective could be to maximize the resilience of the system. I'm not saying that should replace all the criteria that we are using right now, but it could be nicely combined with, let's say, the costs, with some environmental impact, social, and so on. Hopefully, that kind of provides a little bit more explanation.
Yeah, sure. More for sure. It's certainly complicated, I think. And you mentioned the work that you did in Vancouver. What was the response to this approach there? Are they thinking about adopting it? Any more information on that?
Yeah, we implemented this way of thinking in looking the flooding in Vancouver in the context of climate change. So the sea level rise and the flooding of the Fraser were the kind of main hazards, and we try to illustrate the potential utility of the resilience as the kind of decision-making measure. This was a larger scale research project implemented also in 3 other cities across the world. And we got a very positive response to the whole idea of resilience. However, the questions are still, how to merge from the current practice, or how to move from the current practice of, standard-based, code-based type of decision-making to resilience or the process-based. But I think we are entering in, the needs are there. There is obviously a very clear point in the levels of uncertainties we are dealing with. Even NRC is looking into change of the practice of establishing the building codes and so on. I mentioned the work in engineering, the earthquake engineering and so on. I think we got a very positive response for the kind of first time seeing the idea how the resilience can be used. I can tell you that we also got the interest outside of this kind of municipal context, where in a very different way, the BC Hydro asked us to proceed with a very, again, larger scale project to look at the functioning and performance of the hydropower system in serving the purpose and looking the kind of safety in providing the services by switching the whole idea from, the typical safety standards to deterministic simulation combined with resilience. So what we are now looking is a representation of the, hydropower system structure in the form of the very detailed model, and then running the simulations under the various set of potential conditions of failure to generate the outputs that can be represented through the resilience measure or metric. And they are planning to utilize this metric to make the budget decisions that will be dealing with the regular maintenance and renewal of the assets in order to provide the highest level of safety. So I am seeing the interest. I see, our work is being pretty well kind of accepted. And with these two larger projects, the flooding project already completed and the hydropower project currently underway, I think we are already getting closer to real practical application of this concept.
Okay, and so I guess in terms of educating the wider, practicing community on this approach, what do you think is the best way to go? So far you've got a couple of examples, a couple of clients.
Yeah.
Is there, say, a role for the professional engineering organizations to shed some light on this approach?
Definitely. I already mentioned that NRC organized a meeting to see how the climate change can be addressed by, the building codes. And I think they're seriously looking under the funding from the Infrastructure Canada, the really broader context of all different types of infrastructure. And I think the recurring theme during that particular meeting was the need for change. Move from this kind of risk and prescriptive probability-based approach to something new. And I think this idea of the process-based engineering is slowly being introduced, not yet fully formulated, how to implement it. And what I was offering in this presentation and what I think we are offering through our kind of research at Western is this idea of kind of utilizing now the benefits of the systems analysis and the system simulation together with resilience as one way of implementing. I'm sure that can be pretty, or the professional associations, organizations should be and are basically responsible to at least provide the forum for the kind of discussion and possible evaluation of the utility of this approach or modification of it or comparison with other approaches. We have also the regular forms of kind of publication of the work as well as the regular meetings. The last conference of the Canadian Society of Civil Engineers in London in June of last year was under the title Resilience of Engineering Infrastructure. So I think that, you know, from many different levels and points, the need for change is slowly being addressed, and I hope that what we are doing is one potential way to kind of go forward.
Okay, thanks. One last question here, and then we'll wrap it up. So you mentioned the changes that are proposed, or that you have you've submitted a paper on developing data for ungauge stations.
Yeah.
Is there any thought about bringing in, say, IDF data from the northern United States, and is there different approaches in terms of collecting and analyzing this data compared to Canada?
Yeah, that's a good question. I didn't think about that. We were in funding and developing the IDF tool. We were very strongly restricted to, you know, Canadian borders and developing tool for Canadian use. I think that could be a value to investigate the possibility of including some information from the southern neighbor. The tool that I think I mentioned somewhere at the beginning of the presentation from the Cornell University is focusing on the New York State, and I noticed that they did include number of stations in Canada in that particular tool. We use these stations to compare the results with our tool, but maybe something like that can be done on our side to see and incorporate some of the information that may improve our ability to come up with these updates.
Okay, great. So I think we'll end the question period there. And before we sign off, Slobodan, do you have any last comments?
No, I'm very thankful for the opportunity to talk to you today. I did put lots of information in this presentation, but I thought it was important to kind of talk about the tool from the 2 points of view. How to use it, as well as, you know, what we should, or what we are doing to make this tool, or continue making tool, to be relevant to the engineering practice, and explain, you know, why and why we are doing what we are doing. This idea of utilizing the physically based information on temperature relationship with the precipitation was brought as, you know, kind of an idea of more robust solution. We wanted to investigate that to see can that really improve the tool, and that was the reason that I was maybe overwhelming you with the information. I still think we are in a pretty good shape, that at least some assistance is available. Many people that I'm meeting in a professional as well as in the kind of academic setups are talking about this as a useful product that is assisting the practice. And I would like to promise that with the help of ICLR, we are going to do everything in our power to continue providing the best possible service we can. Thank you very much.
Okay, great. Thanks again, Slobodan. Thanks for your time in presenting. And just to let the participants know, we do plan to post this with Slobodan's approval on our YouTube site, so you'll be able to access it later. And just a reminder that our next Friday Forum event will be on April 21st. Sorry, and we'll have Professors Ed McBean and Andy Binns from the University of Guelph talking about the work that we've been working with them on basement flood protection measures, long-term reliability backwater valves. So please watch your inbox, and Tracy Waddington will send a note about that soon. So thanks everyone again, and this concludes the webinar.